This video is an introduction to the new manufacturer component import system in Tas. Tas has a facility to import City Multi, Mr. Slim and CAHV components from the current Mitsubishi catalogue. These real-world components can be modelled to show real-world performance. Much of the year the plant is not operating in peak load but at part load. Furthermore, the efficiency of the plant during operation depends on the condition at the time. Simulation captures this performance. This is a floor plan showing the ground floor zones in the building. As you can see, the space has been broken apart into different thermal blocks. And if we turn on the drawing template, we can see the different systems that have been fitted into the building. The yellow system and the dark green system. And these are each connected to a different outdoor unit. And we can also see where the indoor DX coils are situated attached to these systems. And the same on the first floor, where we have the light green system, the blue system and the red system. And within these systems we can see that there are different zones on different faces of the building. In the 3D view we can look at where the shadows are located within the building. And if we look at the position of shadows moving across the course of a day, we'll see that the zones on different sides of the building will receive solar gain at different times. After the geometry has been exported, we go to the analysis stage and we can choose appropriate calendar to apply to our building. We also select an appropriate weather file, in this case a typical London weather file, and we apply internal conditions to the different types of space within the building. The offices here will be occupied with a varying pattern of occupancy, and the equipment will be turned on at appropriate times to match the occupancy, and the sensible energy gains there will be 8.1 and 11.6 watts respectively. We'll have an outside fresh air rate of 7.4 litres per second per person, and the DX coils will be conditioning the spaces to a temperature set point of 21 degrees. After the building has been simulated, we can view the results visually in terms of the heating or cooling load in different zones across the building, on the ground floor and on the first floor. And if I step through a particular day, we can see that there is initially a heating requirement in the morning, a cooling requirement in the early afternoon, and then in the late afternoon we see a simultaneous heating and cooling requirement on the opposite sides of the building. Now that we've calculated the space heating and cooling requirements, we can model the fresh air supply to the building, which is served by two units, one to the ground floor and one to the first floor. And as I cycle through the zones assigned to each of these schematics, you can see the DX coils that are applied internally to some of the zones. These are associated with 5 cooling collections, one for each of the 5 different circuits within the building. This file has already been pre-simulated to calculate the component sizes, so I can go ahead and import manufacturer data. Starting with the outdoor units, and then the DX coils. Once that's imported, we can review the properties of the imported components, beginning with one of the outdoor units. If I open up the properties dialog for one of the air source heat pumps on the dark green circuit, we can see that the manufacturer name and model number is listed. This particular unit, the PURY P250YJMA, is part of the heat recovery range, and as such, indoor units can operate in heating and or cooling at the same time when attached to the same outdoor unit. This is done via the BC box. The import has set up the type of air source heat pump to VRF with BC box. The capacity and power input varies for both heating and cooling dependent on a number of factors. These include temperature, part load, refrigerant pipe length, and defrost for the purposes of heating. The nominal cooling capacity for this unit is 28 kilowatts. There are then 3 modifier tables that affect the actual cooling capacity during simulation. The cooling capacity correction for temperature plots the correction factors for outdoor dry bulb and entering wet bulb temperature. At an outdoor dry bulb of 25 degrees C and an entering wet bulb of 18 degrees C, the cooling capacity of 28 kilowatts would increase by a factor of 1.05. There are similar modifier tables for cooling power, heating capacity, and heating power. The equivalent pipe length is defined in the refrigerant group. In this case, it's 20 meters. In the airside schematic, we can then review the properties for the imported indoor units. We again see the manufacturer name and model number. A bypass factor has been set up, along with the heating duty, cooling duty, and the fan part load characteristics. With all of this data imported, we can now re-simulate the project. Once simulated, we can review the component level results, which allow us to drill down and see exactly how the system is working. For example, for this DX coil, we can see the hourly heating load and the electrical load of the fan. In the simulation results summary, we can see the annual energy demand and consumption, and in this case the auxiliary refers to the indoor fans. We can also see a weekly breakdown of the cost, and this cost does not include lighting or small power equipment, so this is just the energy cost associated with running the HVAC system. The system we saw earlier, which had heating and cooling simultaneously in the results viewer, was the blue system, and this simultaneous heating and cooling occurs for 903 hours of the year. On the yellow system, it occurs for 354 hours of the year. These are hours in which we can use the heat recovery to recover heat from one zone and supply it to another zone. This model is an updated version of the Chelmsford case study and uses the latest equipment from Mitsubishi Electric, as a result of which we calculate an overall 40% reduction in energy consumption. Thank you for your time and for watching this video.